This is the 8.2 notes on equilibrium. So if we look at this graph, this is a graph of the formation of ammonia gas from nitrogen gas and hydrogen gas. So the first thing it asks us to do is write the balanced equation. So I have nitrogen gas reacting with hydrogen gas, producing ammonia gas. And so balancing the equation, we have 3 hydrogens on the product side, 2 on the reactant side. So put a 3 and a 2 there, and then 2 nitrogens and 2 nitrogens. So we are now balanced. So the next question is, what is changing with time? So if we look at this graph, on the x-axis is time, and on the y-axis is concentration. So over time, what is changing is concentration. Remember, we also abbreviate concentration using the brackets. Okay, so over time, what is decreasing? So if we look at our lines, we have 3 lines on here, and there are 2 that are decreasing or going down. And those 2 things are hydrogen and nitrogen. So hydrogen and nitrogen, or our reactants, are decreasing. What's increasing? Well, the only thing going up is the ammonia. So as this reaction progresses, my reactants decrease as my products increase. All right. And the next question, is hydrogen gas and nitrogen gas decreasing at the same rate? So if you remember rate from math class, rate is simply a change in time. And so in math class, we look at the slope of the line. So of our 2 reactants that are decreasing, we look at the slope of this line and extend it, because that makes it a little easier to see, I think. And then if I do the same for the other reactant, you'll notice that the slopes are not the same. One is more steep than the other. The one that is more steep, so first, they are not decreasing at the same rate. Hydrogen, this top one, is actually decreasing faster. So the hydrogen is decreasing faster than the nitrogen. And you might ask why? Why is that happening? They're both reactants, they're both disappearing. Well, if you look at our balanced equation, for every 1 nitrogen, I need 3 hydrogens to react in order to form our product. And so the hydrogen is going to react, the more of it's going to disappear per time than the nitrogen. All right. The next question, what happens to the right of the dashed line? So here we have a dashed line. And so on to the right side of this graph, you notice all our lines, H2, ammonia, and the nitrogen, all of them have leveled out. So the lines are all level or horizontal. And what that tells us is, as time goes on, my concentrations are not changing. So these are remaining constant. So how much hydrogen I have here is the same as I have here. So this dashed line, when my concentrations are now constant, this dashed line is known as equilibrium. The last question asks, has all of the hydrogen and nitrogen been used up? So once we've reached equilibrium, their amounts are not changing, but are they at 0? And if you notice here, they are not. So they are constant. They're all different amounts, but they are not 0. So no, my reactants have not been used up. They are still present in the reaction container. So when a reaction is almost a complete conversion of reactants to products, when I've changed all of my reactants to products, we say this reaction goes to completion. It'd be easy if that were the case for all of them, but it's not. Most reactions don't go to completion. Instead, they appear to stop before all the reactants are gone. And the reason is that these reactions are reversible. So a reversible reaction is one that can occur in both the forward and reverse directions. So in our example above on the graph, we had nitrogen and hydrogen reacting to form ammonia. The reverse is also happening. My ammonia is decomposing into the hydrogen and nitrogen gases. And so if this is the forward reaction and this is the reverse, I can put them together to create my reversible reaction. a reversible equation. So N2 and hydrogen. And the way I show this, that to show that it's reversible, is to do a double-headed arrow, showing that it can go in both directions. Forms ammonia. So this is a reversible reaction. And reversible reactions will reach that point where the amounts, the concentrations stay the same. And that point is equilibrium. So at equilibrium, the rates of the forward and reverse reactions are equal. So my rates are equal. How fast I'm going forwards is just as fast as I'm going in the opposite direction. But the amounts of product and reactants are not equal. Oops. So again, if we look up at this graph, this is not the same amount as that. It's not the same amount as that. So these amounts are not equal, but they are constant. So the amounts are constant. They are not changing, even if they are not equal to each other. Now, some reactions may have a higher concentration of reactants when they reach equilibrium. Others might have a higher concentration of products at equilibrium, and it all depends on the reaction. So, equilibrium is said to be dynamic because the reactions, the forward and the reverse reactions, are both happening simultaneously at the same time at equal rates. So, macroscopically, in the large view, it looks like no change is occurring, that this reaction has stopped. So if I look at this reaction here, this is actually a glow stick here, and I'm starting out with my reactants, my N2O4. And we'll take a look at this graph right here. I'm starting out again with just N2O4, which is my reactants, and I have no products. My product is NO2. So at the beginning of this reaction right here, I only have reactant and no product. Now, as this reaction progresses, when I get to this point, I have both present now. I have N2O4, this is the N2O4, and I have NO2. And then I eventually get to a point where my amounts of each of these do not change. So this is how much NO2 I end up with, and this is how much N2O4 I end up with. So this is my reactant, and this is my product. So macroscopically, it looks like nothing is changing, that this reaction has stopped. But microscopically, so if we're able to look at the particle level, things are still happening. So my reactants, in this picture, I only have reactants. And then as the reaction is progressing, some of my reactants are turning into these products. Once I have reached equilibrium, I have a certain number of my products, and I have a certain number of my reactants. And this ratio, or these numbers that I have, won't change at this point. I will still have some of my reactant changing into this product, but I will also have products changing back into reactants, and this is happening at equal rates. So the second graph that we have here, so this is the graph of concentration. And so again, my reactant will decrease as my reaction goes on, and my product will increase until they are constant. They don't have to be equal, but they do need to be constant. This is showing my rates. So this is my forward reaction. At the beginning, I only have reactant, and so my reactant is changing into product. And that's the only reaction initially happening. But as I create more product, eventually, this is my reverse reaction, this will start to speed up and my product will change back into reactant until I get to a point where both of these reactions are happening at the same rate. So my reactant is changing into product, but my product is also changing back into reactant at the same rate. So equilibrium is dynamic because the particles are in constant motion and do not actually stop. I talked about the amounts of products and reactants when we get to equilibrium. And this is actually known as the equilibrium constant. It's a numerical value of the ratio of product to reactants. It's unique for every chemical reaction. So, this reaction here that's showing the glow stick will have a different K than the ammonia formation reaction. And so, the way we show equilibrium constant expressions, that's KEQ. It's simply a ratio of how much product I have per reactant, products over reactants. And so if these are equal amounts, which doesn't often happen, then this would be one number over that same number, that would equal one. If I have more products, on the other hand, if at equilibrium I have more products than I have reactants, this number is bigger, then my number is going to be greater than one. If at equilibrium I have more reactants instead, the denominator is bigger, then overall my K is going to be less than 1. So for a given reaction at a given temperature, K will always be constant, regardless of the initial concentrations of my reactants or products. So what this means is in this example right here, if I start off my reaction with just reactants, and so I'm going from reactants and creating products, I will eventually get to a point where I'm at equilibrium. And so my reactants and products are my forward reaction and my reverse reaction are happening at the same rate. Let's say we do that same exact experiment, but this time we start with just product. So I only have product here. And so initially my product is just turning into my reactants. And eventually I'm going to again get to a point where I reach equilibrium and both of these reactions are happening at the same rate. We can kind of think of equilibrium as a line where I have reactants on one side and products on the other. And where I am, the ratio of reactants to products is somewhere on this line. If it's right in the middle, that means that my products and my reactants actually equal each other. And so my K, my KQ, is equal to 1. Usually doesn't happen. If I have more products than reactants when I reach equilibrium, so my products are bigger, I have more products than reactants, then my KQ is going to be greater than 1. If I've reached equilibrium and there's no more change in my concentrations, and I happen to have um, less products and more reactants, say that's reactant favored, so less product and more reactant, then my KQ is going to be less than 1. We can look at this also numerically, although we will not require you to do calculations on this. So this is another reaction here. Here I have hydrogen iodine gas forming hydrogen iodide. And so the first thing it asks us is to identify the reactants and products. So my reactants in this particular reaction, I have hydrogen and iodine, so H2 and I2. And then my products, let me do this in a different color. My products, I only have one product, it's HI. All right. And if you notice, I have 3 different trials. So the first thing it says, what are the initial concentrations of reactants and products? So right here in this table, these are initial concentrations. This is what I have at the start of the reaction. And then these right here, I'll do this in a different color. These are my concentrations once I've reached equilibrium. Okay, so remember, at equilibrium, these reactions are still going on, but it looks like they've stopped. All right, so for trial 1, we look at these numbers. I have reactants right here, and I have a certain amount of reactants, and I'm starting out with no product. So initially, I have all reactants. Oops, sorry, can't see what I'm writing. All reactants. And so on a graph, it might look something like this. I have all reactants and no products. No products. In the second trial, in trial number 2, I have no reactants and I'm starting out with just product. So in the second trial, we have no reactants, as seen here, and we have only products. So our line for our products, or the bar for the products, is a lot higher. And so in the first trial, we had all reactants. In the second trial, we have all products. Now, in the third trial, we look here, we actually have all three of them, and they're all equal amounts. So in the third trial, equal amounts are present. And so I have reactants present initially, and I have products present initially. And what we notice is no matter how I start out, when I reach equilibrium, these amounts are going to be different than these. But if we put it into our equilibrium expression, which is products over reactants, for trial 1, I get a numerical value of 49.7. If I plug these numbers in for trial 2, the equilibrium numbers for trial 2, I also get 49.70. And same for trial 3. Also 49.70. So no matter how I start my reaction, my equilibrium expression is going to be the same for all of them. So the initial conditions don't matter. I will always end up with a certain number of product or reactants and a certain number of products. And you might be asking, why did I draw my products so much bigger than my reactants? Well, that has to do with our KQ. Our KQ, as calculated above, is 49.70. That is much bigger than 1. So KEQ, remember, is products over reactants, and if it's bigger than 1, that means I have a whole lot of products and not as many reactants if it's 49.70.